In this module, we're going to take a look at Meltdown, which is one of the more well-known microarchitectural side channel attacks. So what is Meltdown? Well, Meltdown is an exploit that allows unprivileged user programs to read and leak kernel memory back to an unprivileged process. And it does this by taking advantage of two behaviors of modern CPUs. The first of these we've already seen. So Meltdown uses the CPU cache as a communication side channel. Now, we've already done this in the earlier lectures when we were looking at flush and reload. Now, there are other methods to use the CPU cache as a side channel, but we're not going to go into detail on how those methods work. For our purposes, flush and reload is a very simple and effective way of using the cache as a side channel. Now, the second thing that Meltdown leverages is something that's known as transient instructions. Transient instructions are related to speculative execution. So what is a transient instruction? Well, recall that instructions are executed speculatively. And the classic example of speculative execution is something like this, where there's a slow memory access, and then depending upon that result, there's a branch instruction. And we say the CPU would speculate because it would guess which branch to take, and if it finds out it was incorrect, it would just roll back and go down the other path. But there's actually a lot more speculating going on in the CPU than this kind of toy example, because there's a lot more slow operations inside of the CPU. Floating point calculations, for example, are handled in a dedicated component inside of the CPU. And so to perform a floating point operation, a value needs to get moved into a special floating point register that component can interact with. And then the floating point arithmetic occurs. And then the floating point value must be moved out of that special register back into a general purpose register or memory. And so floating point operations as a whole have not only a large number of instructions, but interact with a separate component. And this is significantly slower than doing just regular integer math that we commonly see on the CPU. Now, how do we leverage something like floating point operations to make something slow or to cause speculative execution? Well, we could have a floating point operation followed by a branch, but let's not think about that. There's something else that occurs, and this is something that's known as a dependent instruction chain. Now, a dependent instruction chain is a series of assembly instructions that rely on each other, right? So if we look here in kind of our classic example, we could say that these three instructions right here, the move RAX plus hex 20, followed by compare RAX 0, followed by jump 0 label, are a dependent instruction chain. And what that means is we can't compare RAX, we can't jump until we know the result of the comparison. And we can't compare until we know the value that was loaded from memory. And so these instructions must be executed in order to concretely perform the operation. And now we could speculatively jump, right? We could speculatively guess what RAX is, but to concretely perform these operations, they have to be performed in order. Now, there is another dependent instruction chain in this example. And that would be this first instruction, move RSI 0, and then move RDI RSI. We cannot move RDI RSI until RSI is 0. If we were to perform this move operation before setting RSI to 0, it would not coincide with the linear execution of these instructions. And so we need to start thinking about assembly instructions in terms of dependent instruction chains. Now, we've already talked about uncached memory access. That's kind of the classic example here, so I'm not going to repeat that. Now, another thing that could make the execution time between individual assembly instructions slow is if the physical CPU core is busy. It could be busy for multiple processes, and so there's a lot of context switching going on. And as a result of that, the wall time in between individual assembly instructions being executed may be longer from the perspective of the process. So why do I care about things being slow? Well, transient instructions are instructions that only run during speculation. And transient instructions never execute during normal program operation. And you'll recall that I mentioned speculation is the default mode of operation. It isn't some special case that only happens when accessing memory and branching. The CPU is speculating all of the time, and it does this speculation by thinking about the instructions as dependent instruction chains. So let's look at this example right here. We have move RAX 0. We then have move RDI leet B. The third instruction says move RAX, move the value that is at the memory address in RAX to RAX. Now, we saw that the first instruction here is setting RAX to 0. So this third instruction will always segfault because it's addressing the memory address 0, which is invalid. And if we think about this example, that should be all that matters, right? Because assembly instructions are executed in order, and therefore we don't have to worry about this fourth instruction because the fourth instruction will never be executed. And in the concrete world, this is true. However, remember the CPU is always speculating, and it's viewing these instructions in terms of these dependent instruction chains. And so if we look at these four instructions, what are the dependent instruction chains? Well, the first would be that RAX must be 0 before we dereference it. That's what causes the segfault. But what is another dependent instruction chain here? Well, move RDI leet B, as well as move RDI byte pointer RDI plus hex F. So I claim that the CPU is always speculating, and within the speculative execution, this fourth instruction may in fact run. Now, it doesn't run concretely. It only runs in the microarchitecture of the CPU. But this is what we're referring to as a transient instruction. It is an instruction that doesn't run in the literal sense, but it does run in the hardware sense. And this is something that Meltdown takes advantage of. When thinking about transient instructions, they don't do a whole lot. They aren't particularly useful. Transient instructions do not impact the architectural state of the CPU. It's not something that we can see during execution. It's not something that impacts the register values. Like, if just because this last instruction was speculatively executed, right, as the CPU was kind of guessing what was going on, that doesn't change the value of RDI. And for all intents and purposes, from the perspective of the running process, these instructions didn't run. So how is this useful? How is this something that we can take advantage of as an attacker? In order to answer that, we have to break down some more assumptions that we have about how the CPU works. So typically, we reason about the CPU executing in order, that it's going to do something like here's instruction 1, here's instruction 2, here's instruction 3, and there is some register. I could point to RIP, RDI, RSI, RDX. These registers physically exist somewhere in the CPU. Like there is a spot that is RDI. And if we zoomed in far enough, I could point you to this is the spot where the RDI value is stored. And it will always be in this physical spot. And that's not necessarily true. In modern CPUs, the assembly instructions that we think of as kind of the lowest level of machine code gets broken down even further. And these instructions get broken down into something that's known as microcode. This microcode flows through various components inside of the CPU. Now, this isn't a microarchitecture class, And so I'm going to do a little bit of hand waving here, but I'm going to talk about some of the components that exist inside of the modern CPU. One of them is something that's known as the reservation station. Now, we can think of the reservation station as like a parking lot. Once the microcode has been created and it's been sorted a bit, the microcode gets placed in the reservation station where it is waiting to run. Now, this is a little bit more detail into how speculative execution works under the hood. Since the assembly instructions were broken down into microcode, these tiny little chunks of microcode are sitting in the reservation state and kind of in a queue. And they all have a dependency chain, very similar to what I was describing with the assembly instructions. And the reservation station will release multiple microcode bits out to go perform a calculation. And so here we see that there's 3, and this is arbitrary. There's 3 pieces of microcode that have left the reservation station and they're going to go compute a value. Now, each of those computations will take a varying amount of time depending upon what exactly the microcode is. When a value returns back to the CPU, to the reservation station, so we have a result, this value goes into something that's called the reorder buffer. And the reorder buffer is responsible for taking that new information, that new value that was returned from microcode, and then updating the reservation station to decide what should the order of things be next. And this happens dynamically in real time as the microcode is being executed. So once X has been passed back to the reorder buffer, the reservation station will get updated so that microcode operation 1 here that was waiting for X is now leaving the reservation station to go compute Z. And we see here that microcode operation 2 is waiting for Z. And so we have inside of the CPU all of these kind of dependency chains of microcode, and the order in which these microcode pieces get executed is somewhat arbitrary. So why does the CPU do this? Well, it turns out adding an additional layer of abstraction, which is like the core of computer science, allows the CPU to do a number of things. It can execute many sequential instructions without having to update a physical register. So if we go back up here and look, in my diagram here, I'm showing more than one assembly instruction being passed into the reservation station at once. And this is, in fact, what happens. The assembly instructions get broken down in kind of batches into the microcode and passed into the reservation station. So then, when this microcode is running and updating values, it doesn't have to leave the microcode world and update a register, because that's actually a lot of work. Instead, it gets translated to microcode where these registers are kind of symbolically there, not necessarily physically there. And the calculations that are equivalent to the assembly instructions then get performed kind of haphazardly based upon the performance of individual hardware components at a microcode level. And so that allows the CPU to execute multiple assembly instructions without having to go back and store a value in a quote unquote like physical register, right? Now, there's another thing that this allows the CPU to do, which I alluded to earlier when I was talking about dependency chains. We say that instructions 1 and 3 depend on each other, and instructions 2 and 4 depend on each other. Well, that dependency is realized inside of the reservation station inside this microcode. And so if we were to think about this, we will have kind of multiple chains of dependent microcode executing inside of the CPU simultaneously, depending upon what subcomponent of the CPU the instruction needs. And so by breaking it down to microcode, the CPU can actually reorder our assembly instructions so that it is always busy. The CPU never wants to be idle. The CPU always wants to be executing something. Now, this last one is a little bit crazy, but it is true. I said that the concept of a register isn't real. Now, there is, in fact, a place in the CPU where you could point to it at a particular point in time and say, this is where the RDI value is stored. However, the concept of registers, like architectural registers, is also just an abstraction in modern CPUs. And so in the event that we are doing some type of branch instruction here, the CPU has the capability to have multiple copies of RAX or multiple copies of RDI. In this particular example here, where we have a branch, there could be two RDI registers. One where RDI is 0 because we did perform this operation, and another RDI register where RDI is not 0 because we did not satisfy this. And the CPU does all of this invisibly under the hood because registers aren't real. What is real is the microcode that the assembly gets translated into. And since all of the microcode is just symbolic representations, it can keep multiple copies of registers and execute based upon conditions simultaneously. And all of this is how the CPU manages to constantly improve without necessarily running it like a faster clock speed. We've been around, 4 gigahertz for consumer max clock rate for quite a while. So where are these performance increases coming from? It comes from parallelization and then smarter algorithms to process these instructions in a more efficient manner. So it's pretty impressive, really, that the CPU can perform all of these changes under the hood, and it's functionally invisible to us as users of the CPU. The CPU essentially still honors that x86-64 architecture design contract. And this allows us as CPU users to think about it in terms of there being a single physical RDI register. We don't have to worry about the fact that there's multiple of them that exist simultaneously sometimes in some scenarios that break down into microcode components that may or may not actually run. We don't have to think about any of that. We can think about it very straightforward as simple users, and the CPU will behave how we expect when we look at it as a user. So is this completely invisible to us? Well, Meltdown takes advantage of the fact that transient instructions exist. So if we have an exploit pseudocode that's running in user land as an unprivileged user here, we have three instructions. The first instruction is going to load the memory address of some buffer. And this can be a user land buffer. This is some buffer inside of the process. The second instruction here is going to try and access a privileged kernel address, some memory address that it is not allowed to. And it tries to access a byte from the kernel. Now, in our traditional kind of view of how assembly is ran, this will clearly segfault. The userland process does not have permissions to access this kernel memory address. And so it segfaults. But now that we've had this kind of discussion about transient instructions, what do we know? Well, this last instruction here is a transient instruction. And so what is this third transient instruction? Well, it says move RDX, RDI plus RSI times hex 1000. And so let's break this down and think about what it's doing. Well, it is going to be taking the byte value that was obtained from the kernel, because RSI and SIL are in fact the same register, right? SIL is the least significant byte of RSI. And so we have a dependency chain here. We have accessing the kernel address and getting the byte into SIL has to happen before this transient instruction. But what else would occur? Well, we have this arrow here to segfault. Well, how does a segfault work? Well, a segfault is a concept that exists in the x86-64 architecture, right? I could type int3, that's an assembly instruction. So the act of segfaulting is something that gets broken down into microcode. And so if we think about what happens inside of the CPU, all of these assembly instructions get broken down into some number of pieces of microcode. And those dependent pieces of microcode get sent out in order from the reservation station. And for the most part, they don't depend on each other. So they can execute simultaneously, depending upon what pieces of the CPU is needed. And so this is functionally a race condition inside of the microcode, whether or not the microcode from the segfault or the microcode from the transient instruction gets passed back to the reorder buffer first. This is a race condition. This is a race condition inside the microcode during speculative execution. So what happens if we win this race? Like, what are we trying to achieve? Well, depending upon what microcode makes it back to the reorder buffer first, the reorder buffer will determine if we should access this memory or we should segfault first. And this is all within the context of speculation, mind you. Concretely, we haven't done anything yet. We may not have even loaded this buffer address into RDI from a concrete execution standpoint. But in the context of speculative execution, we do not have a guarantee that you segfault before this memory address is accessed. And so if we win the race, we will access a byte of memory from this kernel address that we do not have permission to, but we only access it in the speculative context, right? This byte won't actually be in SIL. This byte won't actually be in RSI. I can't print this byte, but I can access the byte within the speculative context. Transient instructions may not change the architectural state of the CPU, but what they can do is load values into the cache. And so if we look at this pseudocode here in assembly, what's occurring? Again, we're loading a memory address of a buffer, and this buffer is something in userland that we do have access to. And we're loading that into RDI. In the second instruction, we're accessing this kernel address that we do not have permissions to. And this is the instruction that should segfault. However, we may have speculatively ran this third instruction. And this third instruction is doing a memory access. By doing that memory access, it's putting a value into the cache. So what does this cache entry's location tell us about the secret value that's stored? Well, let's think about it here. RDI is the base address of a buffer that we are allowed to access. And RSI is a leaked byte from the kernel. And so if we look at this as accessing an array of elements that are hex 1000 in size, the secret byte will be the index into the buffer that exists in the cache. Now, we've already seen how to detect cache hits and misses using flush and reload. So what's different here with Meltdown? Well, Meltdown is placing the value in the cache via transient instructions. We aren't ever accessing this buffer or any index into it in a line of assembly that is concretely getting executed. And so what this allows us to do is leak bytes from the kernel address by figuring out what index into the buffer is in the cache. Let's do a quick demo and see this work. All right, so the demo for this one is going to look very similar to kind of the source code we had for flush and reload. And the reason for that is flush and reload is a big component of the Meltdown exploit. But let's run through the source code here, starting at main. So the first thing that's different is I'm adding a seg fault handler. I'm adding a signal handler. And so anytime a seg fault occurs, this signal handler will deal with it. And the reason that I have this seg fault handler is because if we look at the exploit code itself, while speculatively it may access something that I'm interested in, we know that concretely this line of assembly will always seg fault. And the default behavior when a seg fault occurs is for the process to exit. I don't want my process to exit. I want to be able to repeatedly seg fault. So every time a seg fault occurs, this handler is going to deal with it. What is my handler doing? Well, it's clearing the signal, and then it's jumping back to the exploit code. And we'll see where it's jumping to a little bit later. Now, I'm only registering the signal handler if I provide my program with an argument. And we'll see why in a little bit. As far as setup, I have a setup mem function. This is calling mmap. This is creating kind of the accessible region of memory that I'm going to be using as my communication channel. So this region of memory is 255, and it's 255 because I want to have one page for every possible byte value that I could read. So it's 255 times cache line size, where cache line size is a page. It's hex 1000. Now I'm mapping this region of memory, protected read, protected write, and I'm not writing to it. One of the things that we talked about in a prior lecture was faulting pages by writing to them. One of the things that mmap can do, if you pass the option map populate, is it will pre-fault the pages that are returned. So in this case, the pages that are returned are already backed by physical memory. So this is setting up my communication channel, the setup mem. The secret value that I'm going to try and leak is set up in setup secret. Setup secret is mapping a single page, and it is copying our secret value or secret message to that page. For debug purposes, it's also printing out the value to show that it's there, as well as the address that is being mapped. Next, I've kind of refactored this. So I'm calling a exploit function 14 times. And I'm calling it 14 times because there's 14 characters in the value that I'm interested in. So I need to call this exploit once for every byte that I'm trying to leak. And all I'm doing is passing it the address of the secret. Looking at the exploit function itself, it looks very similar to flush and reload. Now I'm doing a little bit different things as far as how I'm storing values and how many runs I may be doing and what my threshold is. But the actions that are occurring are in fact the same. The primary loop of this exploit is these, 7 or 8 lines. So for every address or every byte that I'm trying to leak, my exploit is going to do 100 runs for that byte. A single run consists of set jump. Now this is the other side of that signal handler. So if the signal handler up here, the seg fault handler, gets called, it is going to silence the seg fault signal and then jump execution back to the beginning of this loop. What else is going on in this loop? Well, we have pre-work, and pre-work is doing the same thing that it did in flush and reload. I'm iterating through a buffer, and I am making sure that the indexes that I'm interested in are not included in the cache. And so I'm just clearing the cache entries right here. This is the flush part of flush and reload. What am I doing in post work? Post work is just like post work that we had with flush and reload, where we have this post work, inner work. We're looping through all of the buffer locations, and we are performing some kind of measurement here. Now, this is slightly modified because I'm keeping my data inside a stats array, but I'm accessing every index of the buffer, and I'm performing post inner work on that index. Post inner work is doing timing right here with time access no flush. Time access no flush, again, we get a timestamp equivalent from the CPU. We try and access what we're interested in. We get another timestamp and we compute the time. So we're just figuring out whether or not something is in the cache. The post inner work is figuring out the access time, and if it is lower than a threshold that I have determined, then it returns true, otherwise it returns false. If we determine that it likely hit the cache, then we are incrementing the corresponding index in my stats array. And so this is just keeping track of that same data, but I'm doing it in a slightly cleaner way. So what's different? What makes this Meltdown? Well, it's going to be this line right here. What I'm doing in between the flushing step and the reloading step. So what's going on inside of speculative exploit? Well, I'm not just directly accessing a value anymore. And that's what we saw in the flush and reload demo. Instead, I have some assembly. Now, this can probably be done in C, but for me, it was easier to pull this off and demonstrate with assembly instructions. So let's run through the assembly instructions that I have here in speculative exploit. The first thing I'm doing is I'm clearing RCX. Next, I'm loading my communication buffer, the buffer that I'm using as the kind of cache channel, into RBX. Now, these next instructions, these next like 6 or 7 instructions, are all related, and they aren't directly important to the speculative element, right? You wouldn't have to have these exact instructions for it to be a Meltdown exploit. The purpose of these 7 or so instructions is to be slow. Let's look at them in a little bit more detail. I'm moving hex 1337 into RAX. I'm then pushing RAX to the stack. I am taking that value from the stack and putting it in a floating point register. I'm then computing the square root of hex 1337. I'm popping that value out of the floating point register from the floating point component of the CPU back into my stack location. I'm then popping that address from the stack into RAX. And then, and this is the most important line, I am dereferencing the result. Now, this will always segfault. Now, the question is why didn't I just put move RAX and then dereference like 12, something that we know is an invalid number? Well, this goes back to what we were talking about with the microarchitectural state and the microcode. Remember when we talked about dependent instructions? Everything right here that's highlighted, the instructions rely on the result of the prior one. And so if the CPU is going to try and process all of these and convert all of this into microcode, it won't know that it's about to segfault until it has performed all of these prior actions. What I'm trying to do is create a instruction dependency chain such that this section of assembly takes longer in microcode to run than the following instructions. And what that will cause is the CPU will recognize that these last 4 assembly instructions, well, they do not rely on RAX. If you'll see, none of these utilize RAX. None of them utilize the floating point register. So they are unrelated to this RAX noise that I have before. And so what the CPU will do is it will speculatively run these steps while it's waiting for the floating point work, because it sees that the result of the floating point math is unrelated to these last 4 assembly instructions. And so these last 4 assembly instructions should get speculatively executed. Now, what is going on in my speculative execution? Well, it's going to load this target address. And I'm doing this after I segfault. In fact, let me show you that I segfault. So we will compile this. All right. And if I run this with no argument, you'll see that I do not register a segfault handler. So that means if I segfault, the program will just exit. And we see that this program consistently segfaults. This isn't like a trick. That is, in fact, what it does. And it segfaults every time. If we throw GDB on this, and we run it, we see that we are at that instruction that I was talking about. Right here, we see that we are trying to dereference RAX and put it in RAX. And if we print RAX, it turns out the floating point square root of 1337 is hex 46. Who knew? But the one thing that we do know is hex 46 is not a valid memory address. And so concretely, we will always segfault right here. But speculatively, the CPU may have ran the following instructions. Even though in GDB, we never got there. Speculatively, we may have ran them. So what are we speculatively running? Well, we're moving a byte from the target address that was specified into CL. And we're using CL because we cleared the RCX register at the beginning. So we know the higher order bytes are 0. Next, we are going to shift RCX left by 12 bits. We're doing this because we want this byte value to be a multiple of page, to be a page multiple. And we're going to add that page multiple to RBX. Looking right here, we see that RBX is our communication buffer. So when I add a page multiple to the communication buffer, the base of that buffer, the result is going to be an address that is a page multiple into the buffer. This last assembly instruction is the line that actually puts the value in the cache. So speculatively, I load the value that I'm interested in. I shift it to be a multiple of the page number, page size. I'm adding that value to the base of a buffer that I do have access. And then I am accessing that index into the buffer. And so what I've done here is I have encoded this byte that I do not have access. It is now represented in the index into the buffer that is in the cache. And concretely, these instructions never ran. You could never run these instructions during normal operation of this program because it will always segfault right here, as we saw. And so that is what makes it Meltdown. Now, in this example, our target address is inside the same process. But that is to keep things simple. In the challenges and in practice, Meltdown is used to leak kernel addresses because those kernel addresses are accessible from inside the userland process. So this exact same code should work if you're trying to leak a kernel address, because you can speculatively access a kernel address. But for demonstrative purposes, it doesn't make sense for me to have a kernel module here to kind of add more complexity to the demo. But we could use this exact same approach to leak values from the kernel. So this is what's different and makes it Meltdown, is that we are accessing the value speculatively. And notice that there is no branch here. The assembly instructions that I'm writing do not have a branch. There's not a compare, there's not a jump. This is just normal speculative out-of-order execution. This goes to show that the CPU speculates all of the time, not just when we're waiting on a slow value and about to branch. The default mode of execution of a modern CPU is to always be speculating. So we saw that the pre-work was flushing. We now have some idea of how to speculatively access a memory address. Our post-work, we already took a look at, but just to refresh, this is setting this stats array. We are incrementing the index for every time that we believe that index was the one that was in the cache from the buffer. This last little block of code here in the exploit function is just looping over my stats array. It's determining what value was most likely cached every time. What value appeared to be cached most often. Whatever index appeared to be cached most often will be the value that we detect. And I'm just printing that number out as a character so that we can compare it against what we know it is, which is secret value. One thing that's worth noting that's kind of unique about my solution, that generally speaking shouldn't be the case, is I am filtering my index here such that the index is greater than 20. And that's because there are some non-printable characters that can get detected in my version of the exploit that I'm filtering out there, where I'm only interested in printable characters in the value that I'm leaking. So now let's see if this actually runs. We'll run it with an argument. And again, the reason I'm passing an argument to this function is so that a segfault handler will be registered. The value here actually has no significance. And what we see is I'm able to very rapidly leak out this value. We see secret message. I don't believe I've seen it be wrong once yet. And so what I have right here is a very solid, quick side channel over the hardware to leak memory. Oh, there we go. So we did have something go awry there. But generally speaking, this is pretty reliable and it's definitely fast. So one last thing I'll show, because I have a feeling there may be some questions, is I'll give you some insight into the values that I am getting in my stats array. Because somehow I'm pretty consistent, aside from this run for whatever reason, but I'm getting pretty consistent results. So I'm going to recompile this where it is printing out the stats data for every index that we're testing. All right, we'll run it again. And so now you can see, as I'm looping through the stats, that most of these indexes were never lower than my cache threshold. There's not a, okay, so there's 179 apparently was quick enough once. 143 was quick enough twice. 101, pretty big winner here. But we see that the signal to noise, it's pretty easy, given the threshold that I have and the number of runs that I'm doing, to detect what was the correct value. Now here is where I have 13 for whatever reason, and I haven't figured out why. In my example code, 13 is a popular index. It's something that I'm doing. I'm accessing index 13 somehow, and I haven't found it. But outside of 13, everything is consistent, right? There may be the occasional 1 or 2 here, but the only indexes that are double digit, which means that they were accessed below my cache threshold, are the correct byte and 13. And we see that that is the case every run. There may be the occasional oddball here, but it is in fact quite consistent and quite fast. So in the demo, I leaked in-process memory using a speculative access. But traditionally, Meltdown is used to leak kernel memory from userland. Because remember, kernel memory is mapped inside of every user process. And so that means if I know the kernel address that I want to access, I can use this same technique where I never officially access that kernel address. I would always segfault. However, speculatively, that kernel information, that kernel memory, could be read and then used to load a value into the cache. Meltdown has been shown to also work to leak data from one process to another. And because Meltdown can be used to leak kernel memory, well, inside of kernel space is physical memory. And so almost, there are like a couple very specific exceptions here, but once you can leak kernel memory, you can leak almost any physical address because the physical addresses are mapped into kernel space. And this can all be done with virtually zero requirements because you saw in the exploit code, the exploit exists as a standalone process. So you write the exploit in C and it is referencing, it creates the situation so that it performs this speculative access. And so this doesn't really require anything other than a vulnerable CPU. Now, practically, you may need more than just a vulnerable CPU. It has been shown and proven that Meltdown works to access values that are not already in the cache. However, Meltdown is significantly easier to pull off. Like if you go on GitHub and find the official paper proof of concept Meltdown exploits, you'll note that all of them preload the targeted value into the cache. It is significantly easier, timing-wise, to be able to pull these off if the value is already in the cache. Now, you may think, well, that makes it unrealistic, but it's not. Oftentimes, program behavior can be triggered that will force it to access a value, right? Think of kernel modules. If you open an exposed kernel module file, it may perform certain actions. And so you could know what the behavior inside the kernel would be. And that may cause it to push or access values, which would result in those values being in the CPU cache. And this would make performing a Meltdown exploit significantly easier. The same thing can be true about other userland processes. If there's a userland process that has virtual addresses that are aliases to something that the exploit code can access, you could influence this other userland process to access that value. Because remember, the cache uses physical memory addresses. Well, the L3 cache does. And so what this means is if one process accesses a physical page of memory or a physical block of memory, and that gets placed in the cache, another process that has a virtual address that maps to the same physical location can end up accessing the cache line entry from a different process. And so this isn't completely unrealistic to say, well, it's a lot easier if the thing that you're interested in leaking is already in the cache. There are ways to encourage program behavior or trigger program behavior in such a manner that this is possible. Now, it wouldn't be fair to not talk about the mitigations for Meltdown. Meltdown has been around for, I believe, 6 years at the time of recording. And patches addressing Meltdown do exist. Now, you'd think, well, this is strange. Didn't I just say that all this requires is a vulnerable CPU? And the answer is yes, but no. So the reason that you can leak kernel memory from user space or from user land is because kernel memory is mapped into the process. And what has occurred now as kind of a mitigation for Meltdown is newer kernels do not map kernel memory into user land processes. Or it's not fair to say that they don't map any kernel memory, but they drastically reduce the amount of kernel memory that is mapped to the virtual address space of user land processes. And what this means is the steps of speculatively accessing something and then communicating it via the cache lines still works. It just means that there is a lot smaller target surface of the kernel to do it against. So the key takeaway here is while Meltdown may not be relevant on updated and patched computers, it's not because this technique doesn't work. It's because they have reduced the target surface area of the kernel to perform this attack against. The core underlying concept of utilizing out-of-order execution in the hardware is absolutely a valid vulnerability that is still relevant today.